Now it's working. Right. All right, so sorry about the delay. Hope you all had a good break. All right, so I've uploaded your next so-and-so thing that's due this week. This will be the last one for 2 weeks because next Saturday the 11th will be your last class test. So like I did in the first one, I'm not going to have a so-and-so thing due the next day that week. So this will be the last one for a while. Okay, now before we get started, you might recall that the last thing we did was we started looking at double integrals. And as I explained, usually the hardest part is working out the limits. Once you've got the limits, and of course you can, provided you can do the integral, you can do it. You might remember that I also mentioned that double integrals are an extension of finding the area between curves that we're used to doing with functions of a single variable. Yeah, so a classic sort of question you might have done in the past, for example, is, maybe something like find the area bound by the functions, I don't know, what y equals x squared and y equals root x, between, so that these intersect at 1 and 1. Now, the way you would normally do it with functions of a single variable, so if you're looking for this area, and you could do it as the integral of right, like so, right, and then do it. You could also think of this as a double integral where you're finding the volume bound by a surface z equals 1 and sitting above this region in the xy plane. And this has the advantage that if you invert these, right, you could think of this instead as a double integral of 1, and let's say I do y first, then x, then y would go from root x, x squared to root x, or I could do it the other way. I could do it with respect to x first, and then you have x going from y squared to root y, y going from, right? So you can also think of double integrals, sorry, before I go there, the advantage here is I can do this integral two ways, and in theory it shouldn't matter. Now in practice it might turn out that one way is doable, one way is not, or one way is much easier than the other. Recognising that is a skill that comes with practice. But the advantage here is I can solve this problem as a double integral, and I have two options on how to do it. You can move up a dimension. Now we can think of double integrals, we can do those two ways. If you move up a dimension, you could think of that as a triple integral of a surface, or I use the term surface loosely, in four-dimensional space. So just as a double integral gives you the volume bound by a surface and that sits above the xy plane, a triple integral is an integral of a function of three variables, which you can't visualise because it sits in four-dimensional space, and the volume, whatever the hell that means, bound by that sits above a three-dimensional region in xyz space. And that integral can be done 6 different ways. And then you can keep going, although usually we stop at triple integrals, but you can keep the idea going. Right, so for example, let's say we were posed this question. Let's say I want to find the volume bound between two surfaces. Right? Now what I could do is set it up as a double integral, find the volume bound by, so that volume that sits in between the two surfaces is like the volume of the upper surface above this, in this case a rectangular region in the xy plane, minus the volume bound by the lower. The difference between the volumes is the volume you're looking for, right? Right, and so you could set this up as a double integral, provided you can find the limits and all of that. This is just a rectangular region, right? And difference, just like what we do with the area between curves of a function of a single variable. Right? But you could also think of this as move a dimension up and think of this as a triple integral of the surface 1 bound by these curves. So if I set this up as a triple integral, and same deal as with double integrals, you work from the inside out. The outer limits must be constant. This is a volume. This is a four-dimensional volume though, so we can't visualise what it is, right? But we can actually calculate it. And of course, if we're doing a triple integral of the function 1, then just like with 3 dimensions, if you've got something that's height 1, the volume and the area are numerically the same thing, right? So the same here. If your function of 3 variables is 1, the volume, 4-dimensional volume, is numerically equivalent to the 3-dimensional volume, right? So you could set this up instead of the difference, and if you do the first iterate, so if you integrate 1 with respect to z, you just get z. Z at the upper limit minus z at the lower limit is exactly what we've got here, right? So if you did this first iterate, this is equivalent to this one, right? But the advantage here is that I can now play with this order. So just like with double integrals, the order doesn't matter. It's dy dx or dx dy, and there's 2 ways we can do it. Here we have 3 things, dx dy dz, and I can stuff around with the order however I like, and it shouldn't matter, provided, of course, I can actually do the integral. All right, so this leads us to a logical extension of triple integrals. Now you can do it with Riemann sums. It's in the unit reader if you're interested. I'm not going to bother with that. And plus we can't visualise what the hell's going on anymore, right? But it's a logical extension of what you do with double integrals of a function of 2 variables. A triple integral of a function of 3 variables is its 4-dimensional volume of something sitting above a 3-dimensional volume. But we can't visualise. We can visualise the 3D volume, but we can't visualise the 4D one. Now here, just like with a double integral, we write them as a double integral of f over region R dA, and dA is the area element in the xy plane, dx dy or dy dx. With a triple integral, we have a volume element, right? Because it's, imagine it's x times y times z, it's like a volume, right? So dv is the volume element. And you can set it up in terms of, prove all the theorems in terms of Riemann sums. but we don't usually do it that way, right? Unless the functions we're doing are very strange. So this is just the formal definition, but we're not going to worry about it too much. One thing we'll use this for a lot, we're going to do this two ways. Either I'm going to just ask you evaluate this integral. It will be a 4D volume that you can't visualise, so you just got to do it numerically. Or if you integrate 1, it's the same as a volume in three-dimensional space. Right? So sometimes with double integrals, you might have a double integral that's very difficult to do in terms of doing x first then y, or y first then x. So this gives you 4 more options on how to calculate the integral depending on the order you want to do it in. And again, just with double integrals, the hardest part, it's not actually that difficult, especially because you could draw, as I explained, when you're solving double integral questions, always draw the diagram you're integrating over, because that will tell you everything you need to know. Same thing here, to work out the limits, we need to work out the bounding curves, but we can't draw in 3 dimensions. This is where it becomes very difficult, right? To figure out the bounding curves is the trick with these ones, right? So, but if I do a triple integral of the function 1, that's the same as the volume, right, of what I'm looking for. Right? So just as double integrals generalise area between curves of functions of a single variable, triple integrals can generalise volumes of double integrals, and so on and so on. But we are going to stop at triple integrals. We usually do. Okay? Right, so to evaluate them, if we're just doing them over rectangular boxes, life is good, right? Because then the limits are all constant, and off we go. Right? So if I've got to find a triple integral of this function over x between a and b, y between z and d, and say z between p and q, then I can do it 6 different ways. Right? And of course you don't have to do it 6 different ways. Right? When I ask you, I do it once. If you've got time and you want to do it a different way to check your answer, because they must, provided you can do the integral, they must be numerically the same. Right? But basically you just play around with the order. All the other notation is the same. You work from the inside out. Generally the brackets are omitted. So when you have you take note of the way it's written, dx dy dz, or dy dz dx, or the order tells you everything you need to know. And you can change the order if you wish, but that gets very complicated because you've got to have to visualise the 3D region you're integrating over. That's where it becomes complicated. Right? And that's the hardest part. And when we get there, I'll show you a trick of how we can do it. Right? But basically the same terminology. So if I've written dz dy dx, that means first we integrate with respect to z, imagining x and y as constant, z from p to q. Then you end up, once you've done the first iterate, z's gone, you're only left with y and x. The second one you're doing with respect to y from c to d. Right, imagining x is a constant. When you've done the next iterate, you've only got x left. The last iterate, you integrate with respect to x. Remember, your answer here must be a number. This is a volume. Granted, it's a 4D volume, unless the function you're integrating is 1, but it is a number, not a function. No such thing as indefinite double and triple or multiple integrals. Right, and again, as usual, the brackets are usually omitted, right? But it's understood that you work from the inside out. Right? Now, basically, first off, I've got an example here. This one I've already given to you, right? Now, if you wanted to change the order of this one, you have to visualise what region I'm asking you to integrate. Oh, hang on, I'm moving too far ahead. Oh, no, it's fine, right? But then this one, basically, this simple line tells you everything. Because you're integrating the function 1, what you're actually doing here is you're finding the volume bound by z going from 0 to 1 minus x, x going from y squared to 1, and y going from minus 1 to 1. Right? And you can change the order if you wish, but that would mean you would have to draw this region, and that's where it gets complicated. Right? So for double integrals, I expect you to be able to draw the region. Triples, I'm going to be a lot kinder. Right? Either it'll be a simple region you can hopefully visualise, things like planes and cylinders and paraboloids and stuff like that. I'm not going to give you something that you have no frickin' idea what it looks like, right? But we won't actually change the order. I won't actually ask you to change the order in a triple integral because you really need to be able to plot it. right? And to do that, it's easiest to use a computer or something like that. Right, but the process is very, very similar. So I integrate one with respect to z, and you just, just a lot more work. Now you've got to do 3 integrals, right? But the hard part is when they're not boxes, right? We've got different regions, and this is where it starts to get a bit, well, figuring out the limits is the hard part, right? So you remember that when we did double integrals, we could think of them as a type 1 or a type 2. And we wrote the 1 and the 2 as Roman numerals with double integrals. So type I and type II, basically. For triple integrals, we use numbers. And there's type 1, type 2, and now there's a third, type 3. Right? So if the region we're doing a triple integral over, which is a 3-dimensional region, is called a type 1 or Z simple. Remember with double integrals we said horizontally simple or vertically simple. Here we say Z simple, X simple, depending on which order you want to do it in. Right, so we say that a triple integral over a region is a type 1 region if it's most convenient to think of the region as bound between 2 surfaces, Z's a function of X and Y. Right? That's what actually, this is what we've been doing with double integrals. Right? Right, so the first iterate is an integral with respect to Z, where Z sits between these 2 surfaces. Right? And then once you've done the first iterate, you're back to a double integral, and then you have 2 choices on how to do that. You can either do it as dx or dy, so x first then y, or y first then x. So visually, what we're doing is this. Right? And it's most convenient to think of the 2 bounding surfaces as normal surfaces of x and y, and we're integrating over a region in the xy plane. The region is called type 2 if it's actually more convenient to integrate with respect to x first. So now we're imagining that we have surfaces x as a function of y and z, and we're integrating this thing over a region in the yz plane. Right? And this is where the visualisation bit becomes a bit tricky. Right? So then you do your first iterate with respect to x, and then your area element is either y then z or z then y. Right? That's what you're doing. You're basically, what is the projection into the yz plane? And then type 3 is, it's convenient to do y first, and you're integrating over a region in the xz plane. So they're all up. There are 6, this can be done 2 ways, there are 6 different ways to do it, all up, right? Some of them might be easy, some of them might be impossible, right? Or they all might be doable, you just don't know, right? So in each of these, there are 6 regions all up, right? And as before, your final answer must be a number. So your last iterate, the outer limits are constants, right? And you do it with sweeps again. Right? There are just 2 small sweeps and then a big sweep at the end. But figuring out the limits is generally the hardest part. Right? Before we get there, so you remember when we're doing, let's have a look at this one. Remember what I said, the way I do it is imagining you sitting anywhere inside, doesn't matter where, right? And if you've decided you want to integrate with respect to y first, you basically do a small sweep in y and then a big sweep in x. Yeah? That's the way I suggested we do it. Right? So you can imagine what you're doing is imagine you're sitting inside this thing, right? And you look up, what curve do you hit? Look down, what curve do you hit? They're your y limits. Yeah? Right, and then you do a big sweep looking far left and far right. Yeah? Or if you wanted to do it with respect to x first, you imagine, what do you hit when you look left and right? We'll give you the small sweep limits, and then your big ones. So the way I do triple integrals is I take this idea and to try and figure the limits out. Right? So let's have a look at an example. So, this is so this is probably going to be about as hard as it gets, right? So let's say we've got something, I've called it a channel weird, whatever the hell it is, right? But it's a solid bound by these surfaces. So I've got Z is the surface x squared minus 1. The Z equals 0, that's basically the xy plane. A plane Z minus 3y equals 0 and a plane 2Z plus y equals 0, right? And if I want to calculate its volume, so I could do this as a double integral, or I could think of it as a triple integral where I'm integrating the function 1. And if I choose my order wisely, I can save work. Now, if I was going to do this as a double integral, like if I asked you this last week, right, this is basically the region I'm looking for. Now, it's a bit hard to see, but obviously the red thing is the parabolic cylinder, right? That's the Z equals x squared minus 1. The blue is the plane Z equals 0. The green is the plane, that must be, that's a third, that must be the plane Z minus 3y equals 0, and then the plane 2Z plus y equals 0, right? Now, if you look at that carefully, right, if I was going to do this as a standard double integral, what's the problem? Right? If I'm near the front, my two bounding Z surfaces, right, so the lower bound is always this parabolic cylinder, isn't it? Right? But if I'm near the front bit, the upper curve I hit is this green plane, isn't it? Whereas I'm towards more the back, right, my upper limit is the purple plane. Right? So if I wanted to set this up as a standard double integral where I'm forcing myself to choose to integrate with respect to Z first, I have to split this region where these two planes meet up at this bit up the top here. Right? Now, it might be easier, right? Because this one I can move around, right? Sort of, right? So you see there's the two planes. So if I'm going, so Z's up. So if I was going to integrate with it, I'd have to split it there, and up near the front, I'd have to integrate Z from between this surface and the lower surface, and then back here it'd be between this plane and this plane. Right? And then the hard part is now I've also got to figure out what is the region in the XY plane I'm integrating over. And the way I imagine that is, imagine I squash this. Right? What does the region look like in the XY plane? Right? You see here, this is where it's starting to get complicated. Right? So this is the way I tackle these problems. Right? What I do is I imagine I'm a little bug and I'm sitting somewhere inside the solid. Right? And now, depending how you've drawn the thing, or you know, if these get very terrible, I give you this diagram. Right? This is not one I would not give you this problem without this picture, right? So, because this one's a bit hard. Right, now I've got X coming, you know, this way. So let's imagine, I don't know, no, that's Y, isn't it? Sorry, Y's coming out, say X is left and right, Z's up and down, right? So if I imagine I'm a little bug sitting somewhere inside this solid, what I do is I'm a little bug and I imagine I look up, what do I see? What surface do I see? I look down, what surface do I see? Look right, what surface do I see? Look left, what surface do I see? Look forward, what surface do I see? Look back, what surface do I see? All right? And so, depending on the diagram, I set it up like this. Right? Right, so if I let's not do up yet. If I'm sitting anywhere inside and I look back, I just see the purple plane, don't I? Right? So I'm looking back in the negative y direction. So y back is the plane 2z, because that purple plane is 2z plus y. That's the same as y equals minus 2z, isn't it? Right? So if I look back, I see y, the plane y, my back y bit is the plane minus 2z. If I look forward, I hit the green plane, right? Which is y is a third z. Yeah? Right, so y front is a third z. Yeah? Now, if I look left, right, what surface do I see when I look left? That means I'm looking in the x direction, the negative x direction, and that's the parabolic cylinder, isn't it? right? I'd see the side of the parabolic cylinder. Now the parabolic cylinder is z equals x squared, so if I solve that for x, that's x equals plus or minus the square root of z plus 1, isn't it? Right? Right, so left is the negative square root, right is the positive square root. Right? Now the hard part. If I look down, so in the negative z direction, what do I see? I just see the bottom of this thingy, parabolic cylinder, right? So if I look down, so z down, or z bottom, or down, however you want to call it, is the parabolic cylinder z equals x squared minus 1. Now z, if I look up, this is now the problem, because this now depends, if I'm this little bug, this now depends where I'm sitting. So if I'm near the front, I look up, I see the green plane. But if I'm more towards the back and I look up, I see the purple plane, right? So the first thing to do is work all of this out. And this is the hardest part, right? So notice the top is, but if I'm sitting between y is minus a third and 0, so that's in this bit here. If I'm a little bug sitting in this right near the front, I see the green plane. But between y between 0 and 2, I see the purple plane. All right, so setting this up, this tells you straight away it is not smart to integrate with respect to z first, because that requires two integrals. All right? So I figure all of these bounds out first. Right? So again, if either the way I give you these questions, either the region you're integrating over will be very straightforward, one I expect you to have not too much trouble to visualise, or I will give you a diagram. Right? So if this was a test or an exam question, I would have given you the diagram on the previous slide. Right? All right, and you figure all of this out first. Okay? And once you've done that, now you have choices. Right? So if you're going to, not that you would, but if you wanted to integrate with respect to z first, that means I'd have two integrals. So z would go from this surface to this surface for y between minus a third and 0, and then this surface to this surface, y between 0 and 2. Ugh, hell with that. Or if I integrate with respect to x first, x goes from this one to this one. Or if I integrate with respect to y first, it goes from this one to this one, right? Or remember, they always go in the positive direction, right? So how you set this up depends how you've drawn the diagram or how I've provided the diagram to you, right? That's not over. It's not over though. Once you've decided your first iterate, you've then got to figure out what is the projection of this region that sits above the plane, the other two planes, or no, the other two variables. Right? So if I decide to integrate, say, with respect to x first, I've then got to figure out what does this region look like in the yz plane? What does its shadow look like, basically? Right? Or if I integrate with respect to y first, I've got to imagine what does this look like in the xz plane. So if I integrate with respect to x first, right, what I'm doing is then I imagine I have to squash this thing in the x directions, and what does that look like? Right? And this takes a bit of skill. It's a triangle. Right? And this is easier to visualise. Right? If I was to, so this is x this way. If I was to squash it, if I squash it, that's triangle is the region that I'm integrating over. Right? If I was to integrate with respect to y first, I imagine I'm squashing it that way, right? So it's a parabola, right? Whereas if I was integrating with respect to z first, and this is a bit hard, might be better from the bottom, right? It's another parabola, right? But actually two parabolas. That one's very nasty, right? So let's work out all the bounding curves. Now, depending on where we're sitting, so this is where I'm explaining if we're the two different z ones, right? So this is all explaining how I figure all of this out, right? So if I project into the xy plane, which would not be the smart thing to do here, right? If I've decided to integrate with respect to z first, for y between minus a third and 0, I've got z going from minus 1, x squared minus, yeah, that's better. X squared minus 1 to 3y, and then y going from 0 to 2, and then the region I'm integrating over looks like that. Right? So if I integrate with respect to z, I imagine I squash this thing in the z directions. What do the bounding curves look like? And they're these two awful looking parabolas. Right, so doing it this way would be nasty. Right? Right, but yeah, I could do it, right? But so I could do it that way. So that is a representation of, now obviously it's the wrong way around, right? But that parabola there, and the way you find them is basically, what have you got? When you go back here, because I've integrated with respect to x first, then it's this one there. I join all of these together to figure out the bounding curves, right? So that's what I've tried to explain all of there, right? But doing it that way, awful, right? But luckily, because I've set this thing up as a triple integral, I have 4 more options, and hopefully they'll be easier. If I decide to integrate with respect to y first, then y goes from, in the positive y direction, from this to this. Then if I'm in the y direction, I imagine I'm squashing it that way, right, to figure out what the shadow of this thing looks like in the xz plane. Right, and that one will give me those limits. So I can do y first, and then the region in the xz plane can either be thought of like this or like this. So in the xz plane, that's what this thing looks like. If I imagine I squash it, so if I go back to this one, I can move around. Right, I'm squashing it that way. Right, so you see it's a parabola and the top, basically. Right, and then, you know, from here I could do, well, now z, if I sit inside, z goes from this curve to this curve, x goes from big sweep from minus 1 to 1, or I could do x going from this curve to this curve, z going from minus 1 to 0. Right, and that's what I've written there. Right, and because square roots are always terrible, that one ain't looking too bad. Right. Or if I integrate with respect to x first, right, that's what, when I squash it in the xz plane, that's what it looks like. Right, so this one, well, this one isn't too bad. I could imagine if I do a small sweep in y going from this curve to this curve, then a big sweep in z going from this here to here, that's not too bad. But if I wanted to integrate with respect to z first, then over here z goes from here to here, and over here it goes from, right, that would split it up into 2 regions as well. So, right, so that one doesn't look too bad. That's requiring two integrals, right? Right, so that's a lot of work as well. Right, so once you've set this up, you can then decide what's the best way to go. Right, and that decision's based on 2 things. You work this out, and then when you squat it, depending on which iterate you decide to do, so basically this is telling you don't integrate with respect to z first, right? Because of the z top bit, it's being split into 2, right? Right, but so that means that now I've got y and z. The next iterate I choose now depends on what they look like when I squash them into each plane, right? When I think of what the shadow looks like. Right? And that's what all of this is figuring out. Right? But in theory, provided you can do the integral, right, it shouldn't matter. Now what I've done, I'm picking the easiest one. So out of all of these ones, this one looks the nicest. No square roots, nice limits, single integrals. Right? Let's do this one. Right? So this says that first I'm going to integrate with respect to y from a third z to minus 2z. And then when I get the double integral, I'm doing a small sweep in z, big sweep in x. Right? So think of it as big sweep, small sweep, even smaller sweep sort of thing. right? But this is a sweep in surfaces, sweep in curves, big sweep, yeah? All right, so if I set it up like that, then this is how I would do the triple integral, right? I'm going y first, then z, then x, right? So if I integrate 1 with respect to y, remember when I do it by hand, I often would put y equals to make sure I don't mix them up. You're free to do that, of course, right? Go through the process, and I get the answer as 56 on 45, whatever that means. So that actually means that's the volume of this region. But I can do it all 6 different ways. Now, I've cheated, right? And I'm getting a computer algebra system to integrate this all 6 different ways for me. I ain't frickin' doing it by hand, all right? So the first one is where I've decided to integrate with respect to z first. Not the pleasant way to do it. The way you read this is, obviously the code here is int is short for integral, right? This is the integral of 1 from z from this curve to this curve, then y from this curve to this curve, then x from this limit to this limit. And I have to split this one, so this is the sum of 2 integrals, and I do it, I get 56 on 45. Do it the other way, you'll see all 6 give me the same answer, right? But doing the actual integral, well, depending on what the functions look like, doing the actual integral is not the hard part. Setting up the limits is the hard part, right? And these ones unlike with double integrals, I might give you one where I want you to reverse the order or do it in a different order. Triples, I won't. I won't ask you to do that. Right? So the question I would give you is one where either you choose the limits or I will give you a diagram so you can figure the limits out. Right? But again, this, just like double integrals is a skill that comes with practice, doing the triple integrals is a skill that comes with a lot of practice because you have to visualise the damn thing first. Okay? Right, now what I would like for you to do is I want you to go through, right, with this diagram. Right? And as I keep saying, if I was to give you this question, I would give you this diagram. I want you to work through this one very carefully and make sure you understand how I got, right, all the limits. I want you to set this up as 6 different integrals. Don't do them, just set them up, right? And make sure you get the same setup as I do, right? So what I want you to do is work through this one very carefully, right? And do what I suggested. Imagine you're a little bug sitting inside. You look up, what do you see? Down, left, right, back, forward. Right? Figure that out first. Make sure you understand where this came from. And then once you then do, all right, I'm going to integrate with respect to z first. What does the shadow of this region look like in the xy plane? Then you've got to figure out, if I'm going to integrate with respect to z first, so the way I've set this thing up, z's up and down, you squash it, what does it look like? Right? If I integrate with respect to x first, I squash it that way. What does it look like? If I integrate with respect to y first, I squash it that way. What does it look like? Right? And make sure you get these 3 as well. Right? And just set it up. Don't do it, unless you want to, of course. Right? And certainly don't do it all 6 ways. Right? But the 2 ways aren't too bad. The way I did it and that way is not too... Oh, no, that's the way I did do it, sorry. That way and one of the other ones, and this way aren't too bad. All right, but make sure you work through this one carefully. This takes a while to get the hang of, right? But you imagine you're sitting inside and look at what surfaces you hit, okay? All right, so make sure you do work through that one. It'll make life much easier, all right? And we'll talk about it again in the next lecture. All right, thanks everyone. I'll see you tomorrow.